Motion simulations. This is when I talked to you the other day about parametrics and how we could simulate real-life problems on it. This is what we're going to do today. So, problem number 1. This is a train problem. 2 trains are scheduled to leave Chicago on parallel tracks. The first train will leave at 12 noon, traveling east toward New York City, a distance of 850 miles at 50 miles per hour. So, your first train, we know, hopefully, that distance equals rate times time. The first train is going 50 miles per hour. I'm going to go ahead and leave this as D, not 850, because I'm setting up my parametric equations next, and I need that to be my x sub 1. So D equals 50 times T. My second train leaves for New York City at 1 p.m., so it leaves an hour later at 55 miles per hour. So we have D equals 55, and since it leaves an hour later, what would we put in the parentheses? T minus 1. Okay, so these are going to be our 2 parametric equations. We're going to say x sub 1 equals 50t, and we're going to say x sub 2 equals 55 times t minus 1. But do you see this y sub 1 equals 1 and y sub 2 equals 2? Okay, well, the purpose of doing this in parametric equations is that we're going to have 2 lines going across our calculator screen, and they're supposed to be the trains. We want to see them separately. We don't want them to be on top of each other. So that's why one of these is 1 and one is 2. I can let it be 10 and 15, just as long as they're not the same number. So on your calculator, make sure you're in parametric mode. Okay, the other thing that you need to do is go, while you're in mode, go down to where it says simultaneous or sequential and change it to simultaneous. For this problem, you need to be in radian mode. Okay, next, go to y equals and put your equations in. So we're going to put into x sub 1, 50t, and x sub 2 is going to be 1. And then we have, Ethan, is there a reason why you're not doing this with us?
My calculator may or may not do that.
Marcus, are you doing this with us?
Yeah.
Where's your calculator?
Right in front of me.
Make sure you're doing it.
I am.
Okay, next, go to your window, and your T-min is going to be 0. We're going to make our T-max 17. Okay, T-max, when you're graphing, if your graph isn't a complete graph, and you know it's not, for example, if you're graphing a parabola and it stopped halfway, that means that your T-max is not big enough, that you don't have enough numbers being plugged in for T to find X and Y, okay? I'm going to 17 on here because you have a train that's going 850 miles, and so most likely it's going to take more than 5 hours. So I'm going to 17, change the t-step to 0.01. I'm going to leave the x-min as 0. Okay, x-max, how far is the train going, the 2 trains? Good, 850. Let's go by 50. Okay, y-min. I'm going to leave it at 0, but my y sub 2, the biggest y value is 2. So let's make that 4 and go by 1s. Okay, so the next thing that's going to happen when you graph this is you're going to have 2 lines going across the screen. So first of all, if you want to stop the graph and start it back up, you hit enter. And then it will stop and hit enter again and it will start. If you want to stop it completely and start it over again, you're going to have to hit on. Okay? So hit graph. Oh, wait. Yeah. And hit enter when you think that they're about at the same position. Is that the same? Okay. Okay, next. We want to know at what time, if you go to the second page, how long until the second train overtakes the first train? So one of the easiest ways to do this, if you can't tell by the x-axis, is to go to your table. Okay, if you hit enter, you cannot go to your table. You're going to have to hit on to be able to go to the table. Then go second graph, and you have a table. Those of you that have the brand new calculators, the whole table shows up. Those of us that don't, we have to cursor over, okay, to get the whole table. Okay, also, if you go to second window, see that table start? That's where my table's starting. If I wanted it to start at 5, I could put 5. If I wanted it to start at 8, I could put 8. Okay, also, see that change in table? Okay, if you wanted to go by ones, you can put 1. And then we want to see where x1 and x2 are the same at what time? T is time. So if you look at 11 and you cursor over, are they the same distance at 11 hours? Yeah. So how long until the second train overtakes the first train? 11 hours. How far are they from Chicago? They're going from Chicago to New York. How far are they from Chicago when that happens? 550. 550 miles. Okay, how long will it take for each train to reach New York City? So what we can do is, on the first train, cursor down until we get to 850. And so how long does it take the first train to reach New York City? 17 hours. Okay, the second train is a little bit more tricky because it's 825 and 880. So something that we could do is go to second table set, change it to 0.5, then go second table, and now cursor down, okay, so it's actually, how long? About how long does it take us to get there? About 16 and a half, right? Okay, 16 and a half hours. So we'll say approximately 16 and a half hours. Okay, we're going to skip D&E so that we have time to get through all this. So go to problem number 2. And I'm also going to go back to table set, and I'm going to change this back to 1. I'm going to change my startup to 5. And you're going to have to be in y equals, so go ahead and go there and clear it out. Okay, next problem says the punter for the Shepherd Blue Jays football team can kick the ball at a velocity of 85 feet per second. Simulate the motion of the punt for several different initial angles. For our purposes, we will ignore things like air resistance and record your findings. Assume the punter hits the ball from the ground. Determine what angle will obtain the best punt. So they've actually given you the formulas, but you're going to have to write your own. So pay attention. X sub 1 is 85 cosine theta times t. This is like kind of like when we did vectors and it was magnitude times cosine theta. Okay, 85 times cosine theta, and it has to be times t. y sub 2 is your velocity formula, acceleration formula. We've learned this in chapter 2. It's negative 16t squared plus velocity times t plus height. So that's what they've done here, negative 16t squared plus 85 sine theta times t plus 0, because it says that assume the punter hits the ball from the ground. So that would be 0 height. You're going to take these two equations and put them in your calculator. Also, if you go to the second page, they want you to do 30, 40, 50, 60. So theta is going to be 30 degrees to start out with. And if it's 30 degrees, then what does that tell me about my mode? Have to change it to degree, right? Okay, and then y sub 1. Go to mode after you have your equations in and change it back to degree. And now we have to look at the window. Okay, so if you look at the window that they gave you T min equals 0. T max is 5. And like I said, if you do this and your parabola only graphs half, then you know that your T max has to be bigger than what you put in there. I'm going to leave my T step. No, change your T step to 0.1. Okay, next, X min, I'm going to leave it at 0. X max. Now, how long do you think a football field is? How? What? I can't hear you. Do you guys not know? 100? Let's do, no. Okay, so let's do this. Let's do 100 and see what happens. Let's go by 25. Okay, Y min, let's do negative 25. And the reason that we do that is so we can, you're going to have a bunch of numbers pop up below your graph. So if you do Y min smaller, then
That's the one on the bottom. That's it again.
so because those numbers pop up, you want to see your graph, so go negative 25. Usually we would just do 0 because we're only working out of the first plot for real life stuff. And your Y max, that's the height. So we'll put 100 in there and see what happens. And let's go by 25 again. And graph it. Not good. Go back. Football field's longer than that.
Oh, no, it's going to be like 300 feet. It's 100 yards. So it's around 300 times.
Is that better? Okay, so now they want to know the distance and they want to know how long it took for the ball to hit the ground. So now go, listen carefully, to trace. Not second trace, just trace. Okay, right underneath the window. Do you see that T? That's time. Now you're going to cursor over. And if you want to make it go jump farther, you can do second cursor. And about how long does it take until that ball hits the ground? What? 2.6 seconds, right? T equals 2.6. Okay, and how? What? What? Well, 6.5 is gonna be the low. And it's not gonna go under the ground, so. No, okay. And then the distance is 191.392 feet, right? Okay, they do 30, 40, 50, and 60. Let's just do 60. So go to window, or go to y equals, and just change that to 60 degrees. Change the 30 to 60. Graph it and see what happens. Okay, we want to know the time. So hit trace, cursor over. Okay, it's about 4.6 seconds that it takes to hit the ground, and the distance is 195.5 feet. Are we okay with that? You see how that works? The distance on 30 degrees was about 100, what was it, 190? 194 or something?
Like 191.39.
Okay, 191.39. Okay, next problem. You're going to have to write the equations. The problem says, in 1990, Cecil Fielder of the Detroit Tigers was at the plate in the top of the fourth of the last regular season game. This would be one of his last chances to hit his 50th home run of the season. The pitcher serves up a fastball low in the strike zone, about 2 feet off the ground, and Cecil hits the ball at a velocity of 150 feet per second at a vertical angle of 21 degrees towards straight away center field. The center field fence, which was 10 feet tall in Old Yankee Stadium, was 408 feet from home plate. Will Cecil hit his 50th home run of the season or not? Okay, so X sub T, first equation. (150 feet per second). Cosine, what's theta? What's the angle measure? Times t. And your second one is the negative 16t squared plus 150 sine 21 degrees times t. And is there a height? Plus what? 2. Good, because it's 2 feet off the ground. Okay, next, let's do this window. T-min, I'm going to let be 0. I'm going to leave the T-max at 5 and do 0.1. X-min, I'm going to do 0. X-max, how far out? 480. So here, hold on, let's do 500. And let's go by 50. Okay, Y min. Let's do negative 25 so we can see what's happening. Y max. That is how high up do you think that ball can be hit? How high up the ball? Not the wall, but the ball. Like, yes. 100 feet? How about 50 feet? Let's try 50. And go by 10. Okay, so go back and put it in. Do your window. Okay, and then we're going to graph it. We're ready to graph?
It's 15 times. A zero in front of the sign. So.
Oh, okay. It should be 155 off.
Oh,
That would probably work. No, that's fine. There you go. Okay, next. They want to know if you hit a home run. So it would be kind of cool to be able to see the wall, right? So to see the wall, we're going to go y equals. Okay, the wall, we want to do how far out, how far from the fence, how far the fence is from the home plate, which would be what? 408? Okay, and then the second one, the height of the wall, which is 10 times T divided by your T max, and our T max was 5. Graph it. Does he hit a home run? Yeah, he does, okay? Okay, next. How long did it take the ball to either get out of the park or hit the ground? So do trace. Right, it takes about 3 seconds for it to be right above the wall. So about approximately 2.9 seconds. And then it says, what would have happened if Cecil had hit the ball at a 10-degree angle? So go back and change the 21 through 10 and graph. Does he hit a home run? No, he drops in the park, right? Okay, what would have happened if Cecil had hit the ball at a bat speed of 110 feet per second? So go back, change it 150 to 110, and change the degrees back to 21. Does he hit a home run? No. Okay, got it? Okay, the Josh Duncan problem, it says Josh shoots a jump, probably is a jump shot, 20 feet straight out from the basket. The ball leaves his hand 8 feet above the floor with an initial velocity of 28 feet per second. That's what's going to go in front, sine, and cosine. It has a takeoff angle of 60 degrees. That's your theta. Assume the front rim of the basket extends 1 foot out from the backboard, and then a shot arriving within a foot behind the backboard at the 10-foot level banks in for a score. So let's do this. Let's go through and put the window in that they gave you. And the X scale and Y scale have to be 1. They have 0. It has to be 1. So T min 0, T max 3, T step 0.1, X min 0, X max 25, X scale 1, Y min 0, X max 25, and Y scale 1. Okay, after you have the window in, Marcus, please stop. After you have the window in, we're going to put the equations in. So go down to C, go to Y equals, clear it out. And the first one is 18 plus T divided by 3. The equation that goes with that is 10. Why do you think it's 10? What is that the height of? Yes. Okay, next one. 22 minus T divided by 3. That's also 10 for Y sub 2. Okay, put the next two equations in. Okay, and notice these equations are written a little bit different than what we wrote them on the other problems because it has 28t in front of the cosine. The t is not behind. And then the negative 16t squared is not in front on the second equation. And that's okay. Does everybody have it in?
No.
Before you graph, go to that x sub 3, and we are going to change that to a ball. So if you have an old calculator, you're just going to hit enter until it changes. If you have a new calculator on the line, you're going to keep hitting enter on the line, I think, or select, and you'll see a ball. Okay? Once you do that, graph it. Does it make a basket?
Yes, it does.
Does he? Yeah. If you want to see it again, go to y equals, go to the y sub 1 and do 10 and graph it. We can also do what we call the ball and chain. So go back to y equals. Okay, hit enter until you get that little circle thing with the line. And hit graph. Okay. Is that pretty cool?
Yes.
That's crazy. Okay, so next. On the back, turn it over.